Hey everyone, today we're diving into something we use literally every single day, but probably don't think too much about: water. But we're not just talking about H2O. We're going to look at the incredible chemical powerhouse that flows from our taps, fills our oceans, and, well, makes life itself possible.
You know those little everyday mysteries? Like, why does the salt shaker get all sticky on a humid day? Or what's that white, crusty stuff that builds up in your kettle? Well, the answers to these puzzles are all about chemistry. And they're not just little annoyances, they're actually signs of some really cool chemical reactions happening right in front of us. So today we're going to break down exactly what's going on.
So here's the plan. We'll start with water's superpower as the universal mixer. Then we're going to see what happens when you push it to its limits and ask, how full is full? After that, we'll get into some weird and wonderful crystals and curious chemistry, tackle the classic household headache of water's hard problem, and finally see how all this science comes together to make our water safe to drink.
All right, let's jump right in with our first section, the universal mixer. Seriously, understanding this is the key to, well, pretty much everything else we're going to talk about.
People call water the universal solvent, which is a pretty epic title, right? And it's totally earned it. Think about it. More things dissolve in water than in any other liquid on the planet. From the sugar in your coffee to the vital minerals moving through your bloodstream, water is the thing that makes it all happen. It's a master at mixing things up.
Okay, so to really get a handle on this, we need to know three key terms. The final mixture, like salt water, is called a solution. The thing doing the dissolving, in our case water, is the solvent. And the stuff that gets dissolved, like the salt, is the solute. So solute plus solvent equals solution. Simple as that. And here you can see it all happening. You've got your solvent, the water. You add your solute, in this case sodium chloride, which is just regular table salt. You mix them together and boom, you have a saltwater solution. It looks simple, but the way those water molecules surround and pull apart the salt crystals is where the real chemical magic is.
So that leads to a really good question. Just how much stuff can you dissolve in water before it just stops? Let's find out in our next section, how full is full. So, at any specific temperature, water has its limits. If a solution is unsaturated, like on the left, it means you can keep adding more solute and it'll keep dissolving. The sponge isn't full yet, but eventually you'll hit a point where it becomes saturated, like on the right. Now the sponge is completely soaked and it just can't hold any more. And this shows you exactly what that looks like. In the beaker on the left, the solution is unsaturated, so the solute disappears into the water. But on the right, that solution is totally saturated. It's reached its max, so any extra solute you add just piles up at the bottom. It has nowhere to go. But here's where chemistry gets really cool, because it loves to break its own rules. There's this special kind of unstable state called supersaturated. This is where you basically trick the water into holding way more solute than it's supposed to. It's like a solution living on the edge, just waiting for the tiniest disturbance to change everything.
So how do you pull off this trick? Well, one of the biggest factors is temperature. This graph, called a solubility curve, shows us how it works. For most solids, as you increase the temperature, that's the bottom axis, you can dissolve more of it. Just look at the line for KNO3, potassium nitrate. It shoots way up. You can dissolve a ton more of it in hot water than you can in cold. Now, temperature is king for solids, but for gases, it's all about pressure. You've experienced this a million times. The fizz in your soda? That's just carbon dioxide gas dissolved in water. At the factory, they use super high pressure to force all that CO2 in. The second you crack open the can, you release that pressure, the solubility plummets, then all the gas comes rushing out.
All right, so let's take what we've learned and see how it leads to some truly curious chemistry and some seriously beautiful results.
So what happens when you take one of those hot, saturated solutions we just talked about and let it cool down? Well, as the water cools, it can't hold on to all that extra solute anymore. So the solute has to come out of the solution. And when it does, its particles arrange themselves into these perfect, highly ordered geometric shapes we call crystals.
Now, some crystals actually have water molecules locked right into their structure, and this leads to two really weird opposite behaviors. On the left, you have efflorescence. That's when a crystal loses its water to the dry air around it and just crumbles into a powder. It's basically drying out. But on the right, you have deliquescence, which is the exact opposite. This is a substance that's so thirsty for water, it literally pulls moisture out of the air until it dissolves itself into a puddle.
And here's what that actually looks like.
On the left, you see those efflorescent crystals turning all powdery as they lose their water. And on the right, that substance isn't melting from heat, it's actively sucking water out of the air to become a liquid. So wild.
And this finally answers our first question. Why does your table salt get all sticky and clumpy on a humid day? Well, it turns out pure salt itself isn't actually deliquescent, but, and this is the key, it almost always has impurities in it, like magnesium chloride, that are. So it's the impurities that are absorbing moisture from the air, making your whole salt shaker wet and sticky. Aha!
Okay, from a sticky salt shaker to a scaly kettle, let's move on and talk about water's hard problem, something a lot of us deal with every single day.
So, what's the difference between hard and soft water? It's actually really simple. Soft water, like rainwater, doesn't have a lot of dissolved minerals in it, so it lathers up really nicely with soap. But hard water, which often comes from groundwater, has picked up a bunch of dissolved solutes, usually calcium and magnesium salts, and those minerals get in the way of the soap, preventing it from lathering well.
And get this, not all hard water is created equal. There's temporary hardness, which is caused by minerals you can actually get rid of just by boiling the water. But then there's permanent hardness, which is caused by different salts that are much more stable. Boiling won't do a thing to them.
So how exactly does boiling get rid of that temporary hardness? Well, when you boil the water, you're actually triggering a chemical reaction. It forces those dissolved minerals to turn back into solid particles, and that is the white, crusty scale that builds up in your kettle. Once those solids have precipitated out, you're left with softer water behind. And all of this leads us to the most important application of water chemistry there is, using this science to make water safe for all of us to drink.
Turning river water into tap water is a massive chemical engineering job. It usually starts with basic filtration to get rid of big stuff like sand and leaves. Then they add something called a coagulant, like a loom, which makes all the tiny suspended particles like mud clump together so they sink and can be removed. After that comes the really critical step, chlorination, which kills all the dangerous bacteria and viruses. And sometimes the water is also treated to adjust fluoride levels for public health. Every single step is a carefully controlled chemical process.
So there you have it. We started with a simple glass of water and ended up talking about solutions, supersaturation, crystals, and giant purification plants. It just goes to show you that behind the most common substance on Earth is some of the most fascinating and important chemistry. You know, water covers over 2/3 of our planet, but after seeing everything it takes to make it safe, it makes you wonder how much of it is truly chemistry ready for us. Definitely something to think about. Thanks so much for joining me.